What if climate change was not something you had to make sense of on a graph or read about in the headlines? What if you could hear it? Global temperatures rising over land. Ocean temperatures warming. Sea levels rising. Climate data is everywhere. It fills reports, charts, computer models. But numbers alone do not always register on a human level.
People believe what they feel over what they think.
Sound works differently. It turns trends into tension. It makes patterns more personal.
What I'm trying to do here is attach feelings to this really alarming situation.
Today we're going off the radar to listen to climate change, not through words or graphs, but through music and sound created directly from the data. I'm meteorologist Emily Gracey, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do. Climate communication has a problem. We have more data than ever before. Satellite measurements, ice core samples, ocean buoys collecting information every second of the day. We visualize it beautifully, and yet for many people, it remains abstract, distant, someone else's problem. But today's guest is taking a radically different approach. Harlan Brothers is both a mathematician and a musician, and he's discovered that when you translate climate data into sound, something remarkable happens. Patterns emerge that graphs can't show you. Trends become visceral in a way that spreadsheets never could. The data doesn't just inform you, it moves you. Through a process called sonification, Harlan is turning temperature records, sea level changes, and atmospheric measurements into compositions that you can actually hear. And in doing so, he's opening up an entirely new sense through which we can understand what's happening to our planet. You'll hear samples of these sonifications woven through my conversation with Harlan. If you like what you hear, you can find all of his sonifications on his YouTube page and his SoundCloud page. Just search Harlan Brothers. Now sit back and enjoy as we explore how sound can communicate what sight alone cannot, and why listening to climate change may be exactly what we need to finally hear its urgency. All right, Harlan Brothers. First of all, great name. I mean, you can't ask for a better name than that.
Can't take any credit for that one.
Well, welcome to Off the Radar. I am so excited to have you on today to talk about sonifications, which is a relatively new term in my brain, but I've gotten to understand it a little bit better over the past year or so. So I can't wait to hear about your sonifications. I want to make sure I get your title correctly. Are you a mathematician and a musician, or you do a lot of different things, right?
That is absolutely true, Emily. Yeah. So those are the two top things. I have a handful of patents. I write songs, and I enjoy doing a lot of different things.
It's interesting because I don't know that people would put math and music together, but there's actually so much about the two of those that kind of are intertwined, right?
Yes, and more, it's easy to find YouTube channels with people who are really, really talented. They know a lot of math, and they happen to be excellent musicians. And so it's something that I think gained a lot more exposure in recent years.
Well, tell me about your background.
I always liked science and math, and I read books about submarines and dinosaurs and laser beams, and I still remember Robert Jastro's Red Giants and White Dwarfs. That was one of my favorites. But I also played music. I took guitar lessons as a kid and was pretty good at it. The science and math, though, still kind of dominated for many years. But then later in high school, I got into playing in earnest and started playing in high school bands, and then went off to the Berklee College of Music to see if I wanted to be a musician. And that was an awesome experience. I really loved that. But the whole science and math thing was never far behind. And after school, even though I was composing and performing in jazz settings, I play guitar, I was still studying. I was studying math and science on my own. The real big shift happened when I came up with some new formulas for the base of the natural logarithm, e. It's a number like pi. It's a constant of nature. It's an irrational number, actually a transcendental number, that goes on forever, right? The decimal expansion never repeats and continues forever. So it's one of those kinds of numbers, and it crops up in nature whenever you're dealing with rates of growth or decay. So it's like pi's not so famous cousin. When I discovered those formulas for E, I had written a brief letter to Scientific American and to NPR Science Friday. I never heard back from Scientific American, but an intern from Science Friday got back to me and said that her husband had read my results, my discoveries, and said that it was warned that it was highly unusual to find anything new in a subject that's been studied for 4 centuries. But then as he read it, he became convinced, and his name is John Knox, and became a great friend and mentor. And we came up with dozens of new methods, published 2 papers in peer-reviewed journals on this, and this is how I got to be a mathematician. So got published, went back to school, and then my professor, Miguel, hooked me up with none other than Benoit Mandelbrot, who is the father of fractal geometry. So fractal geometry, it deals with self-similar objects, things that are in some sense composed of smaller copies of themselves. And it's a type of structure that we find everywhere in the universe, from tree branching systems, tree root systems, river tributary systems, the way you have big branches and smaller branches that come off of those and smaller that they kind of finger out, clouds, galactic structure. The list is really staggering. And they show up in cotton prices. They show up in network structures. So anyway, here I found myself working with the father of fractal geometry. It was the work with Benoit that got me focused on the interplay between math and music, because Benoit was curious about how music can exhibit fractal structure. That, of course, led to composing music with fractal structure, because I was curious as to what fractal music sounded like. So the best way for me was just to compose something with certain known characteristics, and that would tell me what to listen for in the corpus of a music.
What does fractal music sound like?
Fundamentally, we're talking about some aspect of the music that's self-similar. Fractals don't necessarily have to be in space. They can be in time also. And very often, the way they show up is through some kind of statistical self-similarity. A good example, even though it's not music, but it helps to understand what's going on. If you look at clouds, there's a very real way in which clouds are composed of clouds. So they're big puffy balls that are composed of smaller puffy balls, and those smaller puffy balls are made of more puffy balls. They're not exact copies, but in the statistical sense, you find roughly a specific proportion based on how large those little puffs are, or the medium puffs. So you have a few big puffs, a medium number of medium puffs, and then lots of little tiny puffs in the simplest case. So they're not precisely self-similar, but they have a statistical self-similarity. And that is the type of self-similarity that will often show up in music. I don't know if that helps. We can dig a little further.
It helps me realize how much I do not know about music. This is... It's very interesting, but I also think, like, I'm just so impressed by the way that you think, the way that musicians think. I think it's next level. Okay, the sonifications. Can you explain? I think most people don't even know what that term is. And I even saw in something you wrote somewhere that, like, spell check even tries to correct it still.
Yeah, that's exactly it. It is, as you mentioned earlier, a new term of art. It just means that you're going to take some data and you're going to translate it into sound that falls within the human hearing range. And I mention that because it's not necessarily obvious, but for instance, I actually wrote about this. It sonified some data from the Juno space probe that was flying by Jupiter years ago. And so it goes through these radiation and ionization belts. NASA has reams of data of this. Oh, well, it's not a sound. It's radio information, but it's at a frequency that's far higher than anything we can hear. So one of the things NASA data scientists do is take that and they slow it down, like you might in an editor. You can take the way that you could take a bird song, a chirp, 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 and you can slow it down. So it says chirp, chirp, right? It's the same sound, but it's just been slowed up. So if you think of data like the radio information being really, really high chirps that are beyond anything we can hear, you can slow them down and then play them in an audio range. So that's one way to sonify things. Just you can take any data and try to put it into a range that human beings can hear.
It's interesting to me, too, because I did a podcast on sonifications of deep space images. And what was crazy for me that I didn't realize is that that's already data that's been translated. It's just been translated into images that we can see. Either way, it's translating the data. I guess I'm curious about the ability for people to absorb data in that format, because I don't know that I would listen to something and say, oh, those are rising temperatures, or that's a deep space image.
And that's a great question, because it's one of the ways that I believe I'm distinguishing my work now in that particular field, because much of it's super cool stuff, and I can't speak for people who have vision deficits. I don't know how valuable that can be for them. But in general, it's kind of tough. That the stuff from Kim Arcand is brilliant. It's beautiful. It's engaging. It's certainly the best of what that style has to offer. But when you're scanning across an image and turning that image into sound, it's certainly not easy for me, or I think for many sighted people, to, if you didn't have the picture, to understand what it was telling you. So it's interesting and engaging. But what I'm trying to do is to make it easy for people to get what the data is saying. So my thought is to just make it musical. And that's the real challenge, as I write about in my blog, that staying true to the data integrity, and yet at the same time, making it a listenable experience. That's the real challenge, because just taking the numbers and turning them into notes, it can be interesting for a few seconds, but it really isn't anything that's going to, just keep you grooving to the music for a little while. And that is going deeper into the data. It's not going to hold your attention. But the other way is to quantize the information, is to take it and put it into little buckets. If you have a range of 1,000 different notes that are essentially 1,000 different data points, I should say, and they're all very different. They're 0.0123 versus 0.5703, or that kind of thing. There can be a lot of different data points, and it also doesn't sound very musical. That's a continuous sound. So one of the things that some data scientists will do is to take that sound and translate it into notes. And that means what's called binning or coarse graining data. So if I have 100 different notes, I might divide it into 10 bins, for instance. And that would mean that everything that's in the first bin, they're relatively close to each other. And the second bin, they're relatively close to each other. So you make it so that you're getting just 10 different levels of sound instead of 100 different levels of sound. In the case of the climate sonifications that I'm doing, I try to have as wide a range, a musical range as possible, without making it so that the notes are so high that they just sound like little indistinct plinks on the upper keys of the piano, or notes that are so low that they just turn to mud. So there's kind of a sweet range that I try to shoot for around maybe 4 octaves or so in the middle of the piano. But that means that I have to limit the number of bins that I put the data in. Now that does, purists might say, well, you're losing information by doing that. You are losing some information, but not enough information that it changes what the data is saying and what you're actually hearing. You are hearing the shape of the curve, even though there might be a few little bits and pieces that would normally be out of tune if I tried to apply actual notes to them. It then starts to lose its musical appeal. And then I'll take those notes and map them, meaning I choose how those numbers are translated into music by applying them to specific scales. Right? So everybody knows the major scale. You play the white keys on the piano, and that's a C major scale. But there are other types of scales. There are all sorts of different minor scales. There's blues scales. There's a hexatonic blues scale. There are lots of different scales you can use. And that part is simply artistry. That's a question of seeing the data, listening to what the numbers are doing, and also having an idea of what you want to go for. Is this seeming more like a jazzy kind of piece? Is it more classical and dark? Is it a funky kind of Afro-Cuban kind of thing? Now, these are all very arbitrary, and somebody else might map them differently, but my goal is to choose something that makes sense and sounds good. And I do like very much choosing different sounds. So it's not one sound fits all.
In the way that you make it sound good, was there also a thought process of how do I also make this sound alarming or haunting? Because climate change isn't just like pretty sounds, right? So was that part of the process?
An excellent observation, especially with the second one I did. It sounds really kind of ominous. You're watching this graph climb up, and the colors are getting redder. And you have this kind of clang in the background that happens every 30 years. That's poetic license. That's artistic license. Somebody else could make that into a happy dance or something. I don't know, but that's not the way it sounded to me. And so I choose a range, a scale, instrumentation that to me try to get that feeling across, because ultimately it comes down to feeling. People believe what they feel over what they think. We see it time and time again. No matter what you're thinking about something, if you have a different feeling, you're most likely going to go with your feeling. What I'm trying to do here is attach feelings to this really alarming situation. We have a strong current of climate denial still, and to the extent people can get a visceral sense of what's going on, if they haven't themselves already experienced extreme weather, extreme heat, extreme storms, and made the connection on their own, this seems like a really effective, I hope, an effective way of getting that message across.
Are you familiar with Ed Hawkins and the warming stripes?
Yes. In fact, that is indirectly how I came to this, because
I was wondering, there's so many similarities.
A couple of friends, Patrick George is at the University of Ottawa, and Vitaly, he's at Wolfram Research, and they had used a similar approach in programming. So they had these really neat animations of the warming of surface air temperature over land masses, and they were really gripping. They're really cool. And so that's what got me thinking, I wonder what this would sound like. It looks very compelling. How would I turn that into music?
What's overwhelming to people about climate change information is it's like, okay, well, this is a global mean temperature. This is the highs, or this is, sea surface temp. There's a lot of different data. So how to take it in,
It's true. And there's also, once you get into that world, there's so many acronyms there.
So what did you simplify it down to? Did you use global, like average global temperatures?
For the very first one, it was landmass air temperature. That went back to 1950. And I did monthly, I took the monthly chunks and turned it into 31 bins to give me an appropriate range for the music. And I used this hexatonic blues scale, and it had kind of this Afro funky jazz kind of feel. And then I wanted to go back, and because the data goes back to 1750, and that's a lot of data. So then I did it yearly. I made a yearly plot, and it was a little more ominous. I used a harmonic minor scale, and that was 30 bins. It was assigned to 30 different bins. So you might have a couple of degrees change, and that's spread out over 30 different segments, 30 different values that it can take, which I then translated to notes. And then the question was, what else can I do? Because air is not all we're talking about here. And the ocean drives so much of the really scary stuff that's going on now. And so I looked at sea level and sea surface temperature and tried to find time series for that. And that's generally what I want to do for animations of this sort. So I realized that if I combine the actual graph, so not the graph itself, but an animation of the graph as it changes with the sound, synchronized to the sound, then you get the full kind of visceral experience. So I chose the sea level and temperature, and I had this wacky thought that how could I actually turn those into something? Once again, I'm always looking for a different way to translate this data. So it occurred to me that maybe I could make some kind of counterpoint out of it. If I had sea level in one voice and temperature in another voice, that they could play against each other. They're both rising. How would they sound together? And so I tapered the data so it covered the same range. In this case, I believe the sea level data was weekly, so I had to change that to monthly, just average all those weekly values to get a monthly value. So then I had monthly values for sea level and for sea surface temperature dating back to 1993. But they still measure two different things, right? We're measuring height in one of those charts, and we're measuring temperature in the other. So what I did was just to normalize it, meaning over the range of 0 to 1, show what the sea level does when the lowest value that we're measuring at is 0 and the highest value is 1, how it gets from the lowest point to the highest point. And what came out was pretty crazy, and it had this kind of Middle Eastern sound.
Which one changed? I'm assuming they changed at different rates. Like, can you hear different rates going on?
Yes, you do. So I chose, the reason I did what I did is I chose an acoustic bass for the sea temperature, and it has kind of longer, slower arcs. It changes, but it goes up, but in sort of in a more coarse kind of way, just longer arcs. The sea level, on the other hand, has seasonal variation. So it looks kind of almost like a sine wave, but it's at a pretty steep angle because the ocean always changes volume, right? Because the warm water expands, and there are many complicated reasons for this, but it is always going up and down and up and down. But the fact is that trend of up and down itself is very steep.
I'm sure the possibilities are kind of endless here when it comes to what you're going to work on next. Are you going to continue to do kind of this climate sonifications and add more of these? Like, is CO2 going to come into play? Are you going to get methane in there at some point? What are you going to do?
All excellent questions. I'm hoping that as this moves along. I mean, I'm hoping that maybe some true climate scientists can help kind of guide me. I think I'm onto something here. It is different than the other stuff you find, and it is compelling, it seems. The question is just getting it out in front of more people, and I'm hoping that this circle grows and that I will get feedback, because I'm, in this case, I looked at sort of the next obvious thing for which I could find data.
Is this performable?
So yes, some of it is definitely playable. I would love to do that. In fact, I had a Latin jazz band for many years with a bunch of Yale students primarily. We were the number one salsa band in the New Haven area. But I would love to find musicians that would be interested in it. It seems like it'd be a great TED Talk to actually perform this stuff.
Yes. Is there like a scientific equation to what makes music impactful or good or addictive? Like the songs we want to listen to over and over again. Is there like a mathematical equation to how to get to that?
Earworm? What makes an earworm?
Yes, an earworm. Why is my daughter playing Golden from K-pop Demon Hunters on repeat? Why is that song so good? Is there a mathematical reason why that song is good?
I think there have been lots of efforts to analyze this stuff, music sentiment, this kind of thing. I don't know, to answer your question directly, I don't know what that formula is. But yeah, for now, at least, thank goodness, it is something that is firmly in the realm of art and has not been reduced to a formula.
When you see a number sequence, do you hear something?
I don't. My neural circuits are not crossed like that. I don't automatically. Some people, like David Talmud, I think his name, he actually can associate numbers with colors and pick out prime numbers according to what they look like. And so it's not like that. I want to make a distinction, but I do have a sense about them. I feel like I'm like the number whisperer or something. I see a sequence of numbers and I get a feeling about it. And so it's like a sculpture. I kind of start in one place and see where that gets me. What does this sound like? Does this sound like this scale? Does this sound like this style of music? If I add a bass line to it along those lines, does this work? Is this what I'm actually hearing? What does that mean for a drum part? And so little by little, I'll take either the number sequence or the data, whatever it happens to be, and then build a composition out of it.
Do you have any other thoughts on what you want to accomplish and what your hopes are for this?
It's probably not reasonable to hope to move the needle at all on awareness of climate change.
Why not?
Stranger things have happened.
I think, yeah.
So, and I feel I do have a gift. I stand at an interesting point in terms of my facility with music and math. Come on, I'm no Jacob Collier. I'm no Ken Ono in the math world. But I have this interesting blend of skills and this kind of sense about it that drives me to make stuff that people might want to listen to.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes publish every Tuesday. Thank you so much to Harlan Brothers for sharing his talents with us today. You can find all of Harlan's work on his website, harlanjbrothers.com. His YouTube page and his SoundCloud are linked from there. If you're interested in hearing more about sonification, make sure you check out my previous episode about deep space images being sonified. It's called Listen to the Universe, NASA Turns Space Images into Sounds. It was released in May of 2024. Thanks to the National Weather Desk and Sinclair Podcast Group for their ongoing support of the podcast, and to Brian Petrus for his help with today's episode. I'm meteorologist Emily Gracey. Make it a great day.